Alright, today's video lesson is going to cover calorimetry. So we're going to look at measuring heat a number of different ways. Calorimetry is one way of figuring out how much heat is going to be transferred from a system to the surroundings or from a chemical reaction to the surroundings. We'll talk about a number of other ways of doing this, but this is the best way because it's an experimental way. So what is calorimetry? It's essentially the science of transferring heat or measuring heats that are transferring between systems, okay, and surroundings. The calorimeter is the device that we're going to use to make those measurements, okay? All right, so essentially what we're looking at is heat being transferred between the system and the surroundings. So the idea here is that heat is going to be formed or transferred between two objects that are at different temperatures. So if I have two objects, okay, near each other, okay, the idea is that the hotter one, let's actually make the other box red to make it look like it's hotter. The hotter object, which is red, is going to transfer heat to the cooler object. So what's going to happen is that the temperature of the blue object is going to go up and the temperature of the red object is going to go down. So we can see temperature goes down and over here temperature goes up. Now you got to be careful here because temperature is not heat. A lot of students get this confused that they think temperature and heat are synonymous with each other because we see this phenomena all the time that we see heat being transferred and temperatures changing. Well, yeah, it is true that temperature goes down, and it's equally true that the temperature is going up. And what temperature is going to do is the temperature indicates which direction the heat is flowing. Okay, so we can say that the heat is moving from the hot object to the cool object. And this is why they thought that heat was a fluid, because they thought it was moving literally from one thing to another. Okay, so heat is always going to be added to the object. The kinetic energy is going up. So remember, temperature, according to the kinetic molecular theory, is connected to the average kinetic energy. So as the heat moves from this object to the cool object, from the warm object to the colder object, the kinetic energy of these particles speeds up, and therefore the temperature goes up. Transfers, we have to know how objects absorb and release them. And you have some instinctive ideas about this already. You know that certain substances transfer and absorb heat at different rates. So metals tend to release and absorb heat more quickly than other substances. So not everything that absorbs heat is going to experience the same change in temperature. Think about it. If you were to put a pot of water on a stove and you put a metal spoon to the hot water, and then you put a wooden spoon in there and you let the water boil, which one are you going to want to combine and stir the water with? Well, you'd want to use the wooden spoon because it's going to be lower transfer of heat. Okay, we'll talk a little bit more about this heat transfer. I'll show you some examples and give you an idea of how this works. But this is what's called the heat capacity of the substance. Okay, and again, the term is capacity, thinking like, filling things or, things being filled up and having a capacity or the maximum amount that they can hold. That idea is holding over from the calorimetry idea, the fact that they thought that, not calorimetry, I'm sorry, the caloric theory. Okay, that they thought that heat would be putting into things. So metals tend to have a low heat capacity. If you think about it, it means the idea is that it doesn't take a lot of heat to fill it up. So its heat capacity is pretty low. Its ability to absorb and hold on to that heat is rather low. Okay, heat capacity is going to be used with a capital C. We're not going to use this capital C stuff too much, but the idea is that heat is going to transfer when there's a change in temperature, and that's what heat capacity is measuring. We're not going to get into that equation too much. We're going to use another equation you're more familiar with. Now, the greater the heat capacity, the larger the amount of heat needed. So the higher the heat capacity, the more heat it can hold without changing temperature much. And water has a really good heat capacity. We're going to talk about water quite a bit with heat capacities because it can absorb a lot of heat without changing temperature drastically. It has to do with the hydrogen bonding of water and water's strong attraction forces between the molecules. All right, so the amount of substance also is going to have an effect. So that's the other component. So not only are we going to talk about what kind of substance, metals versus woods versus plastics versus rubber materials, but we also want to talk about the amount of substance. Because if you have a little tiny bit of water versus a large amount of water, you know that it doesn't take a lot of energy to heat up the little bit of water. Right? The smaller amount of water will heat up quicker and go up in temperature faster than the larger amount of water. So we know that amount has an effect as well. Now heat capacity doesn't take that into consideration. Oops, doesn't take that into consideration when it's looking at it just looks at really what the type of material is. So we need something a little bit more specific, I guess is a good word to use there, right? Because it's what we're talking about is specific heat. And this is the one that you guys want to know. You want to really focus on specific heat. Now there's two types of specific heat. Molar heat capacity. You know, I'm putting it on here just in case, but you don't really use this much. I don't really see this much in the AP test. You might see a multiple choice question. The idea is instead of using mass, they use moles. So the difference between these two is whether you're talking about moles or you're talking about grams. All right, so we're going to stick mostly with this one right here, the heat capacity of the substance. We're going to use a lowercase c because that correlates with the AP test. I believe your textbook uses an S, so don't get confused on that, but it goes back and forth. To be honest, it's going to be a C. That's usually what chemists use, is the C. S tends to be more for biology, but anyway, enough of that. So the specific heat is a better reference tool because it takes into consideration both the mass and its the specific heat capacity. So I'm not take that back. It incorporates mass in here, so it's just basically the heat capacity throwing mass in here. Now the unit for this is going to be energy, which would be in our Q. Could be kilojoules or joules of some kind, grams times a temperature. So it could be Kelvin or it could be Celsius. Now here, because we're looking at a change in temperature, you can use Kelvin or Celsius. You don't have to use one or the other. You can use either or in this case because we're looking at a change in temperature. Because these scales both they have a different scale, but their changes are the same. So if you jump 1 degree on the Celsius scale, you go up 1 Kelvin. 1 degree Celsius, 10 degrees Kelvin, 10 degrees Celsius. They move at the same rate. So therefore their difference or their change in would be the same. You'll see that in some calculations we'll do a little bit later. A very useful heat capacity or specific heat capacity would be for water. This one comes up quite a bit. You might want to use this or memorize this. Notice that I told you before that this number comes up quite a bit. This 4.184, this is our conversion between joules and calories. Alright, so again we're going to have joules per gram per Kelvin change. Okay? Alright, so let's continue on here for a little bit. Let's take a look at how we calculate. What we do is we have now got a way to measure heat. Alright, so all we need to do is measure the mass of the substance, look up its specific heat, and measure its change in temperature. What we can do now is we can measure those heat transfers. Right? That's what Q is. Q is the heat that's being transferred from a system or to surroundings or system. So we just have to measure mass, change in temperature. We got tools to do that. That's pretty easy. So once we identify what the specific heat is, we now have a very, very easy way to calculate transfers of heat. And this equation also illustrates what I said earlier, that temperature is not a measure of heat. Okay? Because if temperature were a measure of heat, then we wouldn't need this part here, right? Because if temperature were measuring heat, then no matter how much heat I put in, the temperature should change at the same rate every single time. But if I have a larger mass, then my change in temperature goes down. If my specific heat is large, then my change in temperature goes down. So changes in temperature are connected to heat transfers, but they are not the same thing. So you got to get that out of your head. Temperature is not a measure of heat, but a measure of the average kinetic energy. As heat's added, temperature does go up. Alright, so calorimetry. Here we go, back to what we're looking at. Here's what you guys are going to use most often. A very simple, basic calorimeter is essentially just 2 coffee cups nested within each other, okay, or just a single coffee cup. So in the calorimeter lab, we're going to actually use coffee cups and water and all this. So the idea here is this. This is the major assumption you got to realize, is that we are thinking of this as an isolated system. That is a terrible circle. We're thinking of this as an isolated system. What that means is that this is acting as a barrier or a wall between the universe and the coffee cup. Right? So this is acting as a complete barrier, so nothing gets in and nothing gets out. Everything stays in and stays out. So this is supposed to be a completely isolated system. Now you know that there are no real completely isolated systems. That if you have a coffee cup, you put a lid on it, eventually that heat will get through. Right? You know that heat will, because your coffee can't stay perpetually warm. It's going to have to eventually cool off. But what we can do is we can make this assumption become very, very close to true. Think about the ideal gases we talked about first semester. Ideal gases don't exist, but what we can do is we can create situations where the real gases are very much like ideal, right? We can make the temperature very high and the pressure very, very, very low, and under those conditions, real gases become very much like ideal gases. Well, the same thing here. Even though the heat will transfer out eventually, if we do this reaction quickly enough, and the heat doesn't get out right away, right? The heat actually stays in, kind of bounces around for a little bit before it eventually gets out. Well, if we collect our data really quick, we can get this assumption to be pretty fast. So the idea is to get in, get out, and be done. Now, you have to also keep into consideration the fact that we're putting in a thermometer, and we have a stirring rod, and the walls of the container. So there is heat that's going to be transferred. So our approximation is that. It's just an approximation. All right, so here's the basic premise behind this. The heat that's produced in the reaction that we're going to be looking at does not escape the calorimeter. That's our basic premise here. Not completely true, but we can kind of assume that it is. So we're going to say that all of the water, or I'm sorry, all the heat is absorbed by the water. So if we have our system, which is usually our system, let's do a different color like that. The heat from our system is going to get transferred to the surroundings. Okay, all we would do is we'd say, okay, if this is positive, then this has to be negative. If this is negative and this is negative, and we have a negative of a negative, we have a positive. This sign is just a correction value. Now the surroundings is everything in the universe. So when heat is transferred from the system to the surroundings, the rest of the universe heats up. When heat is transferred into the system surroundings goes down in heat and it loses heat. So what we're doing here is we're limiting the surroundings to water. That's the premise. We're making our work a little bit easier so we don't have to worry about all the universe. We can say the whole universe is just the water. And that's the basic premise right here behind calorimetry, is that we are assuming that this equation is true. Is it? Not completely. There are some limits and limitations on that. But what we can do, once we say that the heat transferred from the system to the water, we can then use this equation here. Remember, Q is equal to the famous MC delta T. A lot of students call this the MCAT equation. It's technically not the MCAT equation, but whatever, that's fine if you want to call it that. All right, so what I can say is that the heat of the water has a mass. I can measure the mass of the water, easy enough. I can measure the change in temperature of the water, easy enough. We're going to know the specific heat of water, because we all know it's 4.184 joules, grams, degrees Celsius. Okay, and what we can do is we can say once we calculate this, right, we figure out this portion here, we can then plug that into this equation and figure out what the heat that the system was, or gain, depending on the scenario. And if we know more about the system, we can then break that down into mass, specific heat, and change in temperature. So a lot of times to find this, right, this is going to be something we'll do in a lab, we're going to find what this number is for our system. All we need to do is measure the change in temperature of the system and know its mass. We can then find this unknown value. All right, so that's a lot of stuff to throw at you, so hopefully you got at least enough background. I'm going to go ahead and do a lesson on some calculations with this, and I'll see you guys in class.